I'm delighted to introduce Dr. Glenn Gates, who is currently the conservation scientist at the Walters Art Museum. Previously, he was the head research scientist at the Detroit Institute of Arts, and before that, he was a postdoctoral fellow at the Harvard Art Museum's Strauss Center for Conservation. He also worked in the scientific research department of the National Gallery of Art and the LA County Museum of Art. Glenn received his PhD in physical chemistry at the University of South Florida and a master's in materials engineering from the University of Florida. And today he's going to talk about an ancient mummy portrait examined at the macro, micro, and nanoscale. Please join me in welcoming Glenn.
Thank you. It's really a delight to be here and learn about all of the different interpretations that people have regarding what constitutes active matter. Specifically because at the Walters we have 5 strategic priorities, and the first is to activate the collection. How do you engage people with the works of art in our collection? And I like to think that a good way to do that is to tell stories, and so I like to think of myself as a storyteller. And so Jennifer asked me to share with you this story about some work that we did in collaboration with a whole host of folks at Boise and Iowa Falls concerning the Walters collection of mummy portraits. We're fortunate to have 5 of them. And the one I'll be focusing on today is the portrait of a bearded man shown here. In their original context, they would have been affixed to a mummified individual. You see the portrait mounted here. So I would say that this is the first active state of this portrait. The mummy portraits, there's only about 1,000 of these known. They're distributed through collections, museum collections worldwide. And they represent a portraiture that's of the individual, as opposed to the very idealized representation of an individual that's traditional in ancient Egypt. And so the Walters bearded man came to the U.S. in 1906 by acquisition by Henry Walters, and I would say that's the second active state of this portrait, essentially functioning as a trophy for a collector in competition with Getty, Frick, and other wealthy industrialists. I would say the third active matter state of this portrait is the fact that it allows me to tell a story that really causes inspiration to our visitorship that is really difficult to reach. And so when you think about a visitor in the city of Baltimore that's coming from the neighborhood that was at the center of unrest in 2013, there's 2 things I've discovered that really cause a glint in the eye, and that is armor and mummies. So having a bit of a story to tell about a mummy is the third active state, I would say, of this portrait. There's 1,000 of these known, and they come onto the art market roughly in the 1800s without much information regarding time and place of production. Many of them were grave robbed. There are some that do have provenience. Generally, they're associated with the Fayum Oasis, which is south of the urban areas of Alexandria in the time when Rome invades Egypt, about 30 BC, and they're produced up until about 400 AD. So we have 400 years of production, 1,000 of these things known. And with their acquisitions by collectors in the 1800s, we see a lot of art historical scholarship that's generated because they don't have associations with one another. What we have is a lot of visual interpretation trying to establish family lineages or perhaps similarity of artists. And so to complement this 200, 150 years of art historical or visual analysis, we have coming out of the Getty in 2013 a project that's called the Ancient Panel Paintings Examination Analysis and Research Project, or the APPEAR Project. So this is the brainchild of Marie Swoboda, who's at the Getty Villa. And the thesis is, can we look at the materials these things are constructed from and try and use that information to complement the art historical studies that are in existence for the last several years. And so the first portrait that I looked at was the bearded man. And in collaboration with the head of my department now, Julie Laufenberger, we found some interesting things going on here in the clavi of the portrait. The clavi being the purple marks on the shoulders of a toga that would denote senatorial or equestrian rank, nobility in the ancient world. And think your clavicle bone. And what we saw were these very large inclusions of gem-like purple materials that pretty much everyone in the department was at a loss to explain. They're very large. They didn't seem to be like pigment particles because they're on the order of, as you can see in the scale bar here, 2-3 millimeters in size. So kind of boulders embedded in this paint. They have the characteristic fluorescence under black light that we see very commonly associated with organic materials that are used as colorants, this characteristic pink-orange fluorescence. And we were able to see non-destructively, looking at the elemental composition, that there was enrichment of aluminum and chromium there in these purple particles. And so we started thinking, well, what can we attribute this to? And first off, we thought, well, is this any sort of restoration material? So this is the clavi where we're seeing these inclusions, and you see this this black stuff that covers it. That's the tarry bituminous material that's coming from the mummy. So we know for sure all of this paint is going to be about 2,000 years old. So it's not a modern material. Well, then we started thinking, well, are we looking at some sort of enhancement to the afterlife of this individual? Do they pay a premium in the creation of this portrait to maybe have some sort of spinel or garnet or some sort of added colorant into this area of significance? So maybe some precious stones, an inorganic material. And then we started thinking, well, given the fluorescence, are we looking at an organic material where we're looking at transition metals that are utilized to shift colors of those organics? So with these questions, we were granted permission to sample, which is kind of an unusual event these days at the Walters. And we were able to extract from that sample essentially this very small pigment particle. And so what we have now is an archaeological excavation of that pigment particle, which was completed by a colleague of mine who I met at the Stanford synchrotron workshop that Mark organized, Dr. Joe Butt at the Boise State University attended. He was interested in, as a scientist, getting involved in cultural heritage. So I thought, well, I have this particle. I'm sort of at a loss. I've done everything in-house I can. Maybe you can make some advancements. So it got shipped to Boise, and that was a bit of a challenge, trying to figure out which of the little particles for Daryl to look at. And so he started doing some additional elemental analyses on this, this particle. he was able to confirm the presence of chromium that I was seeing non-destructively. And he was also able to show that it's in the presence of iron as well. But more importantly, was able to show this is not an inorganic species that we're dealing with. This is organic. In fact, we see a very good correlation between the presence of aluminum to potassium. And so, given the information we had from fluorescence and everything else to date, it was highly suggestive that we're looking at some sort of lake pigment material. That is, an artist that likes the color that an organic dye provides, would like to use that in a painting, needs to solidify it somehow. And so there's a way that you can essentially take a dye and put it onto an aluminum salt and end up with a lake pigment, which is understood to be an amorphous hydrated alumina. The process is highly dependent on the presence of what's known as a mordant, that is the glue which sticks the organic species onto the substrate. And generally that mordant is a transition metal, shown here as aluminum. Iron, chromium in the 1800s is also used. And the mordants tend to shift colors of the dye, as well established by Catherine Morales, shown here with Barbara Berry's work, where there's a very good demonstration of the variety of colors that you can get, in this case with cochineal, cast using iron, copper, tin, aluminum as well. And so what we started thinking is this an ancient attempt to color shift a dye? That is, do we have some sort of intentionality to use the presence of chromium to adjust the color? And in order to explore that, we started our archaeological excavation of this tiny pigment particle. And we did that using two different strategies. The first being an atomic reconstruction, and then some essentially cross-sections of this individual particle using transition electron microscopy. So the first work was local electrode atom probe, or LEAP, essentially an atomic reconstruction, which was terribly unsuccessful when we tried to induce a voltage here in order to vaporize atoms at the tip, and then they move to a detector where they're reconstructed. What we did have success with was a laser assisted sputtering, a much more pointed tip. We're able to get some data. It didn't fry the tip. And what we started to see was this. And the significance of this is that what we see is an interface. And it was my understanding going into this that that should not appear, that a lake should be amorphous. It should be the same whether you look at it from the right, from the left, from the top, from the bottom. We should not see interfaces, but yet certainly there's something very significant going on with the iron and also with the lead. We have some sort of interface going on here. So with this data supplied, I was kind of at a loss as to provide a decent interpretation. We knew where the extracted tip came from, didn't really know how deep it went in. So we relied on the cross-section of our pigment particle. And this is the first image. We have two of them. I'll talk about the first. It's coming from the smallest area of our pigment particle. So we probably have the bottom surface and the top surface, and we might be able to see some stratigraphy going on here. But certainly what struck me was the fact that we have differences in density. That is, we have white parts and we have black parts. White parts are going to be high density areas. For example, in here, dark parts are going to be very low density areas. This is two examples of cross-sections from publications of a lake pigment, and you can see that there's really no structure in these things. So it was a bit of a surprise, and I didn't quite know, well, is it just we have such more massive magnification here? So we started looking at what these white materials were, areas of high density. The black areas were, that's where our organic phase is. The white areas, though, it turned out to be very rich in lead. And how to explain the lead? Well, pretty much the only thing that I could come up with is the example presented here by Petrie's excavations, published in 1908, where he has a very nice sketch of a lead-lined vat, where we have areas of probably indigo, blue-black areas, and then red areas. So each one of these cisterns having a different color. So the lead container supplying the lead that we're seeing now in this cross-section. And so I started to think, well, are we seeing some sort of dire sludge being used, some sort of upcycling in the ancient world? And so we have another opportunity to look at that question. And that's shown here. It's a little bit different. It's a different area of our pigment particle where this cross-section is removed. We see something different here, and that is stratigraphy. A very clearly defined area indicated by the green lines. We see actually three different distinct layers. We see this inner layer where we have a high rate of nucleation predominating, but not much crystal growth. Whereas in this outer layer, it's just the opposite. We have crystal growth, but not a high rate of nucleation. Our middle layer has crystallinity in between. And we see something similar here again, as we saw previously, the dark areas being organic, the bright areas being lead-rich. And we were able to now localize where our transition metal, our chromium, is occurring, and that is in this middle layer here. Very difficult to do much characterization of this inner layer because the crystallites were so very tiny. So now that we had some indication of the elements that were present, we wanted to figure out, well, how are they combined? And do that by doing some diffraction, electron diffraction studies in 3 different dimensions. I, of course, did not do this. This was done in Boise. It's extremely laborious. And what we see is something different. In the outer layer, we have a whole bunch of lead carbonates, possibly substituted with a little bit of calcium or aluminum. And something different in our middle layer, where we see lead sulfates. And so the question becomes, well, why are we seeing these different crystallinities in this singular particle? Where, summarizing here, we have very little sulfur in our outer layer, but a whole lot of lead carbonates. Our middle layer, lead sulfate, again, traces of our transition metal mordants, and an inner layer, primarily organic with some contribution of materials, aluminum, sulfur, and potassium. So in the dyeing process, alum is essential, alum being the material which supplies the glue, the mordant that attaches the organic onto inorganic substrate. And I think that's exactly what we're seeing in this individual pigment particle, where we see our dyestuffs being introduced with our alum, and then here in this middle layer, perhaps a different kind of alum introduced, one that contains our transition metals, our chromium. And then finally, the potash, which quenches the reaction and is contributing to the formation of our lead carbonates in this outer surface, sort of the digestion step. So what I'm starting to think now is, again, everything pointing to this dyer's sludge idea. Tried to do some characterization of the organic phase. FTIR ended up burning our material up here. But with the help of Dr. Barry at the National Gallery and Leica M2 filter, have a very good response to anthraquinone. So if we accept my theory that what we're seeing is essentially dyer's sludge upcycled for reuse, it begins to explain why some of the other Appear participants are starting to see in the pink paint, and only in these pink and purple paints, these fibers that are observed on the order of 1 to 2 millimeters in length. So what about this alum? Can it tell us information about our mummy portrait? Well, we know that alums in Egypt come in many different colors, yellows, purples, pinks. These materials have substitutions of various transition metals. But is that chromium significant? So we see in ancient Egypt, we can expect chromium on the order of concentrations of about 50 to 300 part per million. We know that from Sayre's work at Brookhaven. But when I started circulating this idea of can we link the mordant to an area or time and place of production with other Appear participants, Corey Rogie at the Museum of Fine Art in Houston came back and said, well, I found it too. And in fact, she was the only one that's come forward with this. And went to my curator and said, well, I have these two. They have these material similarity. What do you think? And the response was a very sort of washy, well, I could be convinced they were similar time and place of production, but it's not terribly convincing. And so looking at some of the other portraits, here are the Walters portrait of a woman, turns out has also the similar inclusions, but here we see high concentrations of nickel. So I made the request to Detroit and to the Louvre to look at their portraits, to try and see, well, do you also see these high concentrations of nickel, as a way to have a material basis to link these two portraits, which historically have been linked because of visual similarity. And you might be able to see that because of the same medallion used on the two portraits here. Have yet to hear back from either institution, but the Getty was a bit more interested in pursuing this, and so the curator that I work at the Walters had already established some visual similarity between these two portraits. And it turns out that when the Getty supplied a little fragment of the purple paint on Isadora here, it matched the concentrations of zinc that I was seeing on the portrait of a woman. And so we're starting at the Walters now to look at a reattribution of our portrait of a woman to the Isadora master for the Getty portrait. And we like to think about unintended consequences of our scientific research. And this is one of them. At the Boise State University, they introduced this vertically integrated program, which is a multi-semester program which brought together students in art history, economics, chemistry, material science, and the humanities to look at various aspects of lake production in these mummy portraits. So I hope I've provided some evidence to a theory that I have that these mordants are important to examine when it comes to looking at time and place of production of these mummy portraits. And certainly we have a much better understanding or visualization now of our microstructures observed in these lake pigments. They're not expected to be completely amorphous or without structure. And this work would not have been possible without the contributions of the folks out in Boise, my coworkers at the Walters, and funding from the Mellon Foundation. And you might notice in your abstract that I tried to do in 20 minutes 2 different objects. Decided to focus on this one in particular. But the second object is this wonderful Venetian bowl, which I had the privilege to work with Greg Bailey and Ava Heffelstein on, and was not able to get to this here, but it does speak to the theme of this conference, that is active matter, activated, I would say, in 2 different times. So I would direct you to the American Academy in Rome website, where you can hear a 40-minute discussion of the Venetian bowl that I worked on with Greg and Eva, and its relationship or similarity in this idea of looking at pastiches as it relates to Adela Robbia at the Walters. So with that shameless plug, any questions, please?
In the pink or purple paint, was that sludge, is that from the dye stuff, from dyeing, or?
So one of the things that many of the peer participants were reporting was these fibers observed in this pink and purple paint. And it seemed to be an observation that was repeated with several of these mummy portraits, but it was only in this particularly colored paint.
You don't have a theory why?
Well, I think what we're looking at here is the recovery, the upcycling of a dye or sludge.
So textile fibers.
Okay.
Textile fibers.
Do you have any other questions? All right, before we break, I'd like to take the opportunity to thank Glenn again for a fascinating presentation.